Chapter 9.4, we're looking at mathematical induction. So the principle of mathematical induction, so these have to be true. So you let Pn be a statement involving the positive integers n. If P1 is true, and 2, for every positive integer k, the truth of pk implies the truth of pk plus 1, then the statement Pn must be true for all positive integers n. Now, to apply the principle of mathematical induction, you need to be able to determine the statement pk plus 1 for given statement pk. To determine p sub k plus 1, we're going to substitute the quantity k plus 1 for k in the statement pk. So we're going to start to do that first with our example 1, just plugging in k plus 1 and what does that look like. And then that's going to help us in our induction in a little bit. So what we're going to do is we're going to substitute k plus 1 for every one of the k's that we see. So here for s sub k plus 1, this is going to equal k plus 1 squared, and then times k plus 1 squared all over 4. Now let's simplify it just a little bit. And so this is s of k plus 1. And so this is going to be k plus 1 squared times k plus 2 squared all over 4. So that's all we need to do with that one. For this next example, you have s sub k plus 1. So we're going to write this whole thing, 1 plus 5 plus 9 plus plus parentheses 4 times, so k plus 1 minus 1, and then minus 3 plus 4 times k plus 1, and then minus 3. And then let's simplify that as well. So s of k plus 1 is going to be 1 plus 5 plus 9 plus plus, and then if we look over here, the 1 and negative 1 cancel out, so all we're looking at distributing is the 4k minus 3 here, and then plus, this is 4k plus 4 minus 3, so this ends up being 4k plus 1. So let's try these next examples down here. So still plugging in k plus 1. So this is k plus 1 plus 3 is less than 5 times k plus 1 to the square. And so this will be k plus 4 is less than 5 times, and let's go ahead and just to square it, k squared plus 2k plus 1. So it's s of k plus 1 here. Then this example, we're going to do s sub k plus 1 is going to be 3 raised to the k plus 1, and that's greater than or equal to 2 times k plus 1 plus 1. And then so this will be 3k plus 1 is greater than or equal to 2k plus 2 and then plus 1. So s of k plus 1 is 3 to the k plus 1 greater than or equal to 2k plus 3. So try these examples up here. Find the statement. So just plugging in k plus 1 for each one and simplifying it a little bit as needed. Okay, trying this out, you should have gotten for letter A, 6 over k plus 1 over k plus 4. Letter B, you should get k plus 3 is less than or equal to 3k squared. And then for letter C, you should get 2 to the 4k plus 2 plus 1 is greater than 5k plus 5. So now we're going to use mathematical induction to prove the formula here. S sub n equals 1 plus 3 plus 5 plus 7 plus plus 2n minus 1, and that equals n squared for all integers n is greater than or equal to 1. So first, remembering at the beginning, we have to prove that P1 is true. So this is what you write. So 1, when n equals 1, the formula is valid because we plug in, so we're going to plug in s sub 1, and so where that's coming from is we're plugging in s sub 1 to here, and that should equal this first value here. So s sub 1 equals 1 squared, which does equal the 1 there, so that is true. So number 2, so this is what we do next. So we're going to assume that the formula s sub k equals this here, so we're going to plug in k. 1 plus 3 plus 5 plus 7 plus dot, 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 plus 2k minus 1, that equals k squared. We're going to assume that that formula is true, so we need to show that s sub k plus 1, and we're going to plug it in to this here, this value here, is k plus 1 squared. We want to prove that that is true. So here is how we do that. So then, in order to get the s of k plus 1, so we have s of k plus 1. So first we're going to plug in, we're going to write this here. So that's going to be 1 plus 3 plus 5 plus 7 plus dot, 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 plus 2k minus 1. Now remember what we did earlier when we were trying to plug in k plus 1. We're going to plug in k plus 1 where we see the k. So we're plugging it into that one here. So it's plus 2 times k plus 1 here, and then minus 1. Okay, so that k plus 1 is plugged in into this last value here. So then we say s of k plus 1 equals this thing here. Now, what I'm going to refer back to is this here is really s sub k. So we can substitute that first part with s sub k. And then let's finish this on the right. We're going to distribute this. So this is going to be 2k plus 2 minus 1. So let's simplify a little bit. This is s sub k plus 1 equals s sub k plus 2k plus 1. Now remember what s sub k equals. S sub k we said was k squared. So now we're going to substitute that. So s sub k is k squared, and we still have this plus 2k plus 1. Then looking at this, this is factorable. This factors to k plus 1 squared. And so therefore we prove that it is true. If we put in k plus 1, we do get this value here. So by mathematical induction, this formula is valid for all integers n greater than or equal to 1, or all positive integers. So try out this example here. Use mathematical induction to prove this formula, doing the same thing we did with the example 2. So when you try this out, you plug in n equals 1 first of all, and the formula is valid because when you plug in 1, you get 5, which is true, right? You plug in 1 here, you get 5, which is the first term here. Now you assume that the formula s sub k, you plug in k for it, equals this k times k plus 4 is true. So assume that's true. We're going to show that k s of k plus 1, and you plug in k plus 1, we should get k plus 1 times k plus 5, that is true. So then you write everything here. You write the s of k plus 1, plugging in each piece, and then remembering you're adding the k plus 1 into this term here. And then you substitute this first part, and then simplify and multiply out, and you see that you do get this back. So combine the results of 1 and 2, we can conclude by mathematical induction that the formula is valid for all integers n is greater than or equal to 1.